This video covers example 1 for the 3.1 notes. So we already started talking about the definition of relative extrema. There is one thing I want to add. Relative extrema exist on open intervals. Since it's an open interval, that means that it cannot be at the end point. So relative extremes cannot be at endpoints on the graph. Endpoints of the graph. So for example, if I have something that looks like this, and there are clear endpoints here, this endpoint is an absolute min, but it is not a local or relative min because it's at an endpoint. This point here is a relative min because it's not on an endpoint and it's still the minimum value in an open interval around it, for example. Okay, so relatives, mins, and maxes only exist at endpoints. Let me erase this so we have some more space to work. All right, let's look at some examples of what characterizes the derivative at a relative extrema. So let's take a look at this f of x. We could use the quotient rule to take the derivative, but that's going to take a little while. We might want to use, just multiply this out and simplify. So we would have 9x squared minus 27 over x cubed. That's a cube. Okay, and then split it into 9x squared over x cubed minus 27 over x cubed. That's going to give us, well, the square cancels out, so we have 9 over x minus 27 over x cubed. It's the same thing as 9x to the negative 1 minus 27x to the negative 3. All right, we're ready to take the derivative. So f prime of x, derivative of that would be negative 9x to the negative 2 minus 27 times negative 3 times x to the negative 4. That's going to give us negative 9 over x squared plus 81. This is going to be 81 over x to the 4th. So that's the general derivative for this function in A. The question is, what's the derivative at the relative maximum that we have right here at x equals 3? In order to find the value of that derivative, we're going to plug in 3 for x here. So let me erase this so we have a little room to do that. All right, so f prime of 3, so the derivative at this relative maximum is going to be, let's put it here, negative 9 over 3 plus, 3 squared, because it's squared here, x squared, plus 81 over 3 to the 4th. Negative 9 over 3 squared, well, 3 squared is 9, so this is negative 1, plus 3 to the 4th is 81, so this is 81 over 81, which is 1, so it adds to 0, which makes sense. The derivative is the slope of the tangent line, and the tangent line here has a slope of 0. Okay, let's take a look at C, and then we'll go back to B. In C, we have a relative minimum at 3 pi over 2, and we have a relative max at pi over 2. Let's find the derivative so we can see what the slope of the tangent line is. All right, the derivative of f of x here, the derivative of sine, is just cosine of x. So if I want to find the derivative at pi over 2, plug in pi over 2. Cosine of pi over 2 is, think about the unit circle, cosine of pi over 2. It's the x value here. The x value is 0. So cosine is 0. All right, that means the horizontal tangent, the derivative, the slope here is 0, which makes sense. Let's do it for 3 pi over 2. Cosine of 3 pi over 2. Again, it's the x value, but down here, so we have 0, negative 1 at 3 pi over 2, so it's 0. So it doesn't matter if it's a maximum or a minimum, the slope of the tangent line or the derivative is going to be 0. Okay, now we saw two examples where the derivative is 0. It turns out that a derivative that's undefined at a point can also indicate that there's a relative min or max. So let's take a look at example B. Let me erase this. Okay. In example B here, we have the absolute value function. It can be defined as a piecewise function, negative x, so this part, for x less than or equal to 0. And then positive x for x greater than 0. If we take the derivative of each part, if we take the derivative of negative x, we get negative 1. And that exists for x less than 0. If we take the derivative of positive x, we get 1 for x greater than 0. There's a problem though. Here at 0, we have a slope or a derivative of negative 1, and we have a slope or derivative of 1. What's going on at 0? Well, the derivative there is undefined because the derivative is different from the left and from the right. So, f prime of 0 is undefined. But we know that there's, sorry, not a horizontal line. We know that there is a relative minimum here. So it's possible to have a relative minimum where the derivative is not 0, but instead is undefined. Okay, so let's summarize that. So on the next page it says, note at each relative extrema, so whether it's a relative max or relative min, the derivative is either 0 or does not exist. The x values at these special points are called critical numbers. So we have a critical number if f prime of c equals 0, so its derivative is 0, or it's not differentiable, so the derivative is undefined at that value. Then it's called a critical number. Here are two more examples. So in this picture on the left, the derivative for this left-hand side is going to be different from the derivative on the right-hand side. And that means the derivative at c does not exist. So c is a critical number because the derivative, f prime of c, does not exist. Here on the right-hand side, we have a horizontal tangent where the derivative is 0. So c is also a critical point here. So we get this summary where it says, if f has a relative min or relative max at x equals c, then c is a critical number of f. It's important to note that there can be critical numbers where there is no min, relative min, or max. So I could have a critical number because the slope of the line, the derivative, is 0, but there isn't a relative min or max. And here's an example for this. If I have a line that looks like this, there we go. This point here is called a point of inflection. The slope here of the tangent line is actually 0. So f prime of c equals 0. But it's not a relative min or a relative max. So it's possible to have a critical number, but for it to not represent a relative min or max. On the other hand, all relative mins or maxes has a derivative that's not defined at that point, or where the derivative is 0. All right, for the next example for guidelines on finding extrema in a closed interval, you can move on to the next video.